Ready?
You want the laser or?
Well, we got the laser, we just,
No,
that would change the size.
no, it won't change.
Okay.
Are you all set? Maybe, is there a need for you all to be bunched up there? Should one stand over there, maybe? All right. Clock is ticking.
All right, good afternoon, we're Team EMech. My name is Michael Lorenzo, this is Eduardo Garcia, and to the far left is, far right is Francisco Uriarte, and we're here to present the magnetocaloric test bench. We're going to jump straight into a little bit of a technical background of what our device is supposed to do. On the right, you can see a classical vapor refrigeration cycle, which is primarily used in domestic applications or in your car. It's how your AC works and your refrigerator works. You start with a decompressed gas, as you can see on the right. On the left is the magnetocaloric material, which we will be testing, which is not magnetized. Once the gas is compressed, the temperature increases, as on the left with our material. When we magnetize the material, the temperature will increase. We will remove the heat while magnetized, while the material is magnetized, as in the refrigeration cycle, you remove the heat while the gas is compressed. And then once we demagnetize the material, we'll get a decrease in temperature, which is lower than the initial temperature that we started with. And then you repeat the cycle. Now the reason we did this research is because the current refrigeration cycles, they use gases, they use hydrochlorofluorocarbon carbon-based gases, which are harmful to people, potentially harmful to people who come in contact with it, and they're harmful to the environment. Now the solution to this problem is potentially magnetic refrigeration. The only problem with magnetic refrigeration now is that the solid materials which exhibit the most magnetocaloric effect are very expensive. They're single crystalline structures. For example, one is gadolinium, which is about $700 for 100 grams of this material. So this would be a very inefficient replacement for what we have today. Now the reason for designing and manufacturing this test bench is to aid in the research of polycrystalline materials which will exhibit the same magnetocaloric effect. So this device is to take material specimens, magnetize, demagnetize, remove the heat as I showed you in the cycle, and put them through the effect and measure the temperature of the material. And then the material can be replaced with different material once as it is developed, and it will help develop more cost efficient materials which can be used in this new type of refrigeration cycle. Eduardo's going to go over some of our preliminary designs and the design of our device.
All right, so we went through about 5 iterations of the design. Here you can see some of the first designs that we did. This is a rotational design, which the piece is moving around. This is the piece. This is another rotational design that we did with a sphere going around. This is a linear motion. Also, there's very different ways you can go about going through the magnetocaloric cycle and the magnetocaloric refrigeration cycle. So we were looking for which one would be the best method to design it to be able to have something viable. So you can see the problem with these designs is that the material is moving itself. So what we did was our final design, we went with a rotational system. So you can see here, this rotational system does not move the piece is stationary, and what we moved was the magnetic field. The magnetic field goes around the materials, and it demagnetizes it that way, instead of actually moving the material itself. The reason why we did this was because it was very hard to acquire the heat transfer required when the material is moving around. So this system, as you can see, is a rotational system. It has multi-planetary gear trains. It's got 5 gear trains inside of it. Custom designed and manufactured heat exchangers. So you can see them there in the prototype. Custom centrifugal pumps, 2 of them, a hot pump and a cold pump. They're both designed. Everything is driven off a single shaft, so a single motor drives everything, all the gear train, all the heat exchangers, cams, etc. And we have synchronized rotational motion because we have to synchronize the outer magnets to the inner magnets and also synchronize the inner channels from the pumps to be able to distribute the flow. Here, this is an example of one of the gear trains, which you can see is up top here. Pretty much this is the gear train that moves the magnets, the outer magnets, and they have a 2.8 to 1 reduction gear ratio. Now, due to cost, we had them ABS printed. We did stress analysis on them, and we have 2.15 safety factor on them, so we're sure that they won't break with the stresses that are being put on it. Also, the heat exchangers, they actuate up and down via spring and cam system. Pretty much the cams were timed so that it goes by as the cam goes by as the magnetic field just it's about to be demagnetized, so it goes by and removes the heat. And the top cam is offset from the bottom cam to be able to keep its timing and synchronization. Here you can see the pumps. The pumps are actually, it's kind of hard to see here because everything's a bit cluttered, but we have the bottom pump is the cold pump, and then the hot pump is on top, which this was the hot pump. The hot pump here, you can see the planetary gears inside of it. They're very small, so you can see it there, but pretty much this is 3 inches in diameter. So we had to fit 2 planetary gears inside this one. There's one here and another one in the bottom. Now the reason why we had to design pump was because due to the design constraints, and as you can see due to the size, we couldn't find any pump that would actually fit in there to perform the job that we needed. Also, there's 16 total heat exchangers. 8 of them are on the hot side, and at any given time, the flow and any of the heat exchangers cannot touch each other. You can't mix the heat because one may be on the cold cycle, the other one may be on the hot cycle. So due to that, we had to have inner channels, and the inner channels distribute the flow from one inlet to the other outlet, but at the same time they do not mix from one to the other. So that's another reason why we had to design custom pumps as well. The impellers, pretty much they were designed by us as well. The whole pump was designed by us. The cold pump is a similar design as the hot pump, except the only difference is that we can mix the flow in the cold pump, and then it picks up the working fluid, the cooling fluid from a reservoir in the bottom, you can see right down there. Alright, so the pumps, we did some calculations on them. Assumptions were the cooling fluid is incompressible. We're using water to cool the heat exchangers. The fluid velocity at the impeller tip is equal to the velocity at the impeller tip. That was the assumption that we did, that the fluid would move with the same velocity as the impeller did. And also, the minimum rotation speed required to attain turbulent flow and be able to have enough heat transfer was 81.3 RPMs. Here you can see some calculations on the timing. Pretty much at 300 RPMs impeller speed, which is the max that the test bench would rotate. The channels inside the pumps would rotate at 107 RPMs, so the 2.8 reduction, and the velocity of the channels is 0.33, and that will give us 0.04 seconds of opening for the flow to go out of the pump. Now we calculated that, and that was enough, assuming 80% efficiency of the pump. So with that, we still said that the pump was viable. And then the slowest speed, as I said, was 81.3 RPMs, and that allowed for 0.17 seconds of the flow, for the flow to transfer, which is the minimum required to maintain turbulent flow.
I'm going to be going over a few theoretical results. They're mainly simulated results. I'm going to be going over magnetic effect and heat exchanger. I'm going to be going over these because these are basically the essentials needed in order to perform the refrigeration cycle for our apparatus. Here we see the first slide for magnetic effect. For the magnetic effect, we used 5mm by 5mm by 1mm motor magnets. They have a pull force of 2.5 pounds each and a flux of 1.24 Teslas. Now the way we simulated this, we ordered them in a circular pattern like this. There are 4 rows here. You can't see them because, I guess, of the simulation results. There are 1, 2, 3, 4 magnets stacked just like that. And similarly over here. And we are going to introduce the magnetic material that we are to test into the magnetic field. Here we use SolidWorks for the simulation. We averaged a flux density of 0.636 Teslas at the center, since the center would exhibit a weaker flux density. We wanted to see what was the flux density at the center. That was our main concern. And here to the right, we wanted to see what would happen if we were to shift, as per our design, we wanted to shift the magnets 5 degrees counterclockwise. And we wanted to see what was the flux density at the center. And as expected, it was a little weaker. The flux density at the entering, at the center, which is this piece right here, that magnetic piece, is 0.5 to 0.6 Teslas. And the average flux density leaving of the leaving piece, which is this one, is 0.33 Teslas. And this shows promising results for the refrigeration cycle to actually occur. The next is the heat exchanger. This is a typical diagram, the diagram that we mainly focus on. On one end of the is the heat exchanger. We only focus on the copper plate. It's a thin copper plate. And on this side would be the ferrous materials that we are to test. A couple of assumptions that we made is we treated the material as a heat source. Seeing as though in future simulations that we will see, in order for the actual heat transfer to occur, it's a very small window period. So we're going to treat, so for that matter, we're going to treat the material as a heat source. And on this side, we have natural convection, being air. And on this side, which is the heat exchanger side, we have forced convection due to the pumps, and that would be water. Next slide. All right, so these are transient thermal analysis done on SolidWorks. Here we treated, as I said earlier, we treated the magnetic material, the first material, as the heat source. For the simulation, we assumed a temperature change of 5 degrees. So the magnetic material is exhibiting 303 Kelvin, which is 5 degrees above room temperature, which we assume to be 298 Kelvin. And this is the starting time. This is at time 0.05. And as you can see, at time 0.05 seconds, there's already a temperature gradient going on, starting at the center of the copper piece. It wasn't until 1.25 seconds where the entire temperature, please excuse the color difference, but as you can see there, or maybe you can't, but everything there is at equilibrium temperature. Everything here reached 303, and that was at 1.25 seconds. So that gave us an idea of how our system would theoretically be operating. Next slide. However, those simulations weren't including the effect of water, of forced convection. So this simulation right here proposes the idea that water would be entering through this port right here at 298 Kelvin. And as you can see, in a time frame of 1.25 seconds, which was what was constrained in this video, the exit temperature of the water did reach a value of approximately 303 Kelvin. That was very promising. You can see the same cut plot right here. The water at 1.25 seconds reaches an equilibrium of 303 Kelvin. Next slide. The previous simulations didn't include the test material, which acts as the heat source, as I said earlier. So here we include the heat source, which would simultaneously heat up the copper plate as well as the water passing through it. Now, the water does not reach a value of 303, probably due to some resistance in the material, between the contact of the material and the copper piece. However, we do achieve a temperature increase of at least 1.5 Kelvin. Next slide. Now, initially, with nothing on our paper, we assumed a budget of 3,000. That's what we assumed on the entire project, the assembly. However, we didn't choose the materials that you see there. Most of those materials are plastic materials. Initially, for example, the pumps, we wanted them to be aluminum at first, mainly due to the fact that they hold better or tighter tolerances. So we decided to max out at $2,000. So we wanted to reconsider our design, and we changed materials. So most of it is plastic now. So we looked at about 1,500. Everything actually came out to be 1,380, and I'll show you how that is distributed. One more time. Here's the major parts and components, including motor, pumps, magnets, and their subcomponents. That averaged out to about 927.61. Next slide. The minor parts and components, which accompanied the major parts and components, 258. Next slide. And the tooling costs, which includes bits and mills, which was almost $200. Next. 30% of our project is 3D printed due to the size constraints and intricate designs of our products. 70% were hand machined or machined by us. And we estimated 1,200 work hours total manufacturing time between the three of us. Future considerations would include finalization of our prototype and develop and perform test procedures on multiple ferrous alloys in future. Any questions?
When you said finalization of the prototype, what is not done on your prototype today?
Mainly, what we wanted to do is be able to physically capture data on the test pieces and to plot them on a user-friendly interface to be able to see the actual temperature changing in real time and to see how the refrigeration process is taking place and how it's taking place. Right now,
Have you gotten any data?
As of now, no, we were not able to acquire any these ferrous alloys. What we did accomplish was the actual finalization of the mechanics of the prototype. So we'll be showing you that shortly.
Okay, so explain to me, you said you're moving the magnetic field?
Yes.
Maybe I'll just sneak in really quick. Can you just step it through? I know you guys did the actual kind of theoretical process, but just step through everyone exactly what happens in the machine itself.
Yeah,
So
so-
what happens? Yeah.
All right, so you can see here, this right here, that's this plate right here holds the outer magnets. Inside, the inner magnets are aligned with, as you saw in the simulations. Now, this is going to rotate, and this holds. It's going to be in two of the test pieces. One of the test pieces is going to be starting its magnetization phase. The other one's going to be, already magnetized and is going to be going through the heat exchange. So then it gets demagnetized. That's when it cools. And that's when it cools down and it produces the cooling properties. So
Hang on, just really quick. Just think about it as one of the pieces of the test material. Okay, so what happens? One piece of test material, the magnets come along, right?
Yeah.
So that piece of test material gets magnetized. So start from there. So just focus on that one piece.
all right, so so this test material gets magnetized by the outer magnets and the inner magnets. Then the cam that you see right there would come and actuate the heat exchanger down. That would remove the heat from the magnetization, right? Now, after that, it gets demagnetized, right? It gets demagnetized, and then the bottom cam would actuate the bottom heat exchanger to remove the cooling as the temperature drops from its original room temperature. And pretty much it just cycles through.
So the question I asked from that is, why didn't you use electromagnets? Where you have no moving parts, but you've got an electrical field that you basically...
Because it takes a whole ton of energy, that's why. So these are...
More than this?
Well, the whole point of this is that it's solid state. So these magnets are rare earth magnets. Basically, you don't have to put any energy into the system other than rotating those magnets to get cooling. That's it. So it's really, really efficient process. I guess I'll step through it really quick. So the material itself, right, it's at ambient temperature.
Yeah.
You then magnetize that material. So that material increases in temperature, so it goes up 5 degrees, something like that, right? You adiabatically remove that heat. So that's where that first heat exchanger comes down, takes away the heat. So now it's magnetized and it's at room temperature. So the second you remove that magnetic field, the demagnetization happens and it becomes a loss in temperature. So you get 5 degrees Celsius cooling based off of just rotation of this magnet around the material. So that cooling has to be taken away somehow. So they take it away by putting a cold side heat exchanger up. The water or coolant or whatever is in there comes off, and it's 5 degrees cooler than whatever the ambient temperature is. That can be used to cool whatever you want to cool, your car, your refrigerator, whatever you want to do. Then finally that has to go back up to ambient temperature, so they get it back up to ambient temperature just because it will return to ambient temperature during that process. I know it kind of is a roundabout process. I know we go back and forth a lot with these guys, but they understand the process, I know for sure. They just had a little bit...
Nervousness.
well, I think they... anyway, it is what it is. You guys did it.
So how close are they to having this function?
It's very close. What we need now is just, as you can see, there's about 300 individual pieces to manufacture associated with it. So these guys have been in Rick's shop for about a month and a half just manufacturing. The other problem that we have is the current materials that actually have really registered changes in temperature are about $3,000 for that individual piece. So I am working on a separate research project to try to make it cheaper, but right now they need it functional before I go and buy a piece of that material to try it out. No offense to the guys in there, but so they're very close. I guess is the answer.
And you're excited?
Yeah. I mean, so the whole,
I get it.
again, they did a good
That's
job.
good,
But the whole
guys.
thing is, so all sorts of different applications can use this, right? I mean, I don't mean to. You guys should be answering questions, so I don't want to jump in. But in space, if you have refrigerant, almost every spacewalk is because they have coolant leaks. Almost everyone. So in this case, there's no coolant, so you don't have that leak. The atmosphere, ozone, whatever it is, right? The ozone is majority of the holes in the ozone are from refrigerant. So that's where. Anyway, I'll let them answer this. Sorry.
You done? Where are the global elements in this project?
Well, the fact that we have the entire system running off of one rotating shaft it's very efficient. You can just any device that has a rotating element, you can sap a little of that rotational energy and implement some cooling.
No, global elements. I mean, how is this adaptable worldwide? And how did you address that in your project?
Well, a few studies show that magnetic refrigeration, just the refrigeration, not this apparatus, is about 30% more energy efficient than your average home refrigerator. So there's been a few studies around worldwide, mainly in Europe actually, that have developed these magnetic refrigerators and seamlessly have been distributed commercially. So one of the global impact I would suggest is that it would eliminate, hopefully in the future, as our goal, eliminate the use of harmful refrigerants, which are almost all of them have a value of ODP.
Right.
And
So how did you address that? Is there a slide on that in your?
Yes.
Let me see that slide again.
so at the beginning. So a lot of these gases are hydrofluorocarbon and hydrofluorocarbon based. This is harmful to the ozone layer. The most widely used refrigerants have a high ozone depletion level. Actually, the most efficient refrigerants today have substantially high ODP. So the objective of this project is to be able to test these different multi-crystalline materials to see which one acts efficiently as other magnetic materials such as gadolinium. However, as you know, commercial grade gadolinium is still very expensive. It's about $700 per 100 grams.
Okay, the reason for my question was the global elements was a very explicit evaluation component, and your response to that is implicit, and so you need to recognize that. You follow what I'm saying?
Yes.
All right. No other questions? Thank you so much.